Hi everyone. So we are going to talk about manifold learning. We are from group 3 and there are several things that we will be delivered. First, introduction, and second, manifold learning and manifold learning algorithm, and the advantage and disadvantage of manifold learning. So in many data analysis tasks, we can be confronted with a very high dimensional data, and this data can be very difficult to visualize. So in order to get the better vision of such data, the dimension must be reduced. High dimensional datasets also can be very difficult to visualize, and a number of techniques have been developed to reduce the dimension of the data. PCA is probably the most popular dimensionality reduction method. It finds the direction along which the data has maximum variance. However, this is linear methods, and these linear methods may fail to recover the intrinsic manifold structure when the data manifold is not a low-dimensional subspace or an affine manifold. Nonlinear principal component analysis, or NLPCA, is a nonlinear generalization of standard PCA that actually can be used to reduce the dimensionality of the data. To create a better understanding, we use mixed-Swiss roll dataset in 3D projection. So this dataset was created to test out various dimensionality reduction algorithms. The idea was to create several points in 2D and then map them to 3D with some smooth function, and then to see what the algorithm would find when it mapped the points back to 2D.
Okay, to prove our previous points, we will compare the PCA with manifold. We will try to reduce the dimension of the Swiss roll dataset by using PCA first. PCA, although it is one of the most popular dimensional reduction method, it may fail to recover intrinsic manifold structure, which could happen in nonlinear dimension. In this case, we are going to use two different PCA methods. The first one is with kernel RBF. We can see that the data points are separated, but it is not clearly separated between the clusters. As we can see, we can only see clearly that the yellow cluster is at one point, but the other cluster are not clusterized properly. We will try another method, which is using kernel poly. As we can see that this is actually even worse than the last method, where most data points didn't get clusterized clearly. This is why that although both methods are able to reduce the dimensionality, we cannot cluster the data well. This is where manifold learning came to be another option to reduce the nonlinear dimension so we could clusterize the data better.
Okay, so what is manifold learning? Manifold learning is an approach to nonlinear dimensionality reduction. Algorithms for these talks are based on the idea that the dimensionality of many datasets is only artificially high. Manifold learning implements the following things. First is clustering, unsupervised learning, dimensionality reduction, semi-supervised, supervised, given label, and unlabeled point, build a labeling function. So manifold learning algorithm, there are various techniques for nonlinear dimensionality reduction. The typical techniques include isomap, locally linear embedding, Laplacian agent maps, Hessian agent maps, diffusion maps, spectral embedding, multidimensional scaling, and TSNA. But in this example, we will use two most popular algorithms, namely isomap and TSNA. Manifold learning algorithm, the algorithmic process of most of these techniques consists of 3 steps. First, a nearest neighbor search. So we have to define the value of key. And then a definition of distance or affinities between points. and an agent problem for embedding high dimensional points into a lower dimensional space. Okay, the first example is the distributed stochastic neighbor embedding, or TSNA. TSNA converts affinities of data points to probabilities. The affinities in the original space are represented by Gaussian joint probabilities, and the affinities in the embedded space are represented by student t-distribution. There are some parameters that we have to add for optimization. We want to reduce the dimension into the 2 dimension only. The perplexity is defined as k equals to the power of s, where s is the Shannon entropy of the conditional probability distribution. The perplexity of a key site is key, so that key is effectively the number of nearest neighbor TSNA considers when generating the conditional probabilities. Larger perplexities lead to more nearest neighbors and less sensitive to small structure. After that, we can just call the fit transform, include the X data to the method. After that, we visualize the result of the TSNA algorithm using index 0 and 1. So in the scatter plot, as we can see, data distributed in the cluster is good. This algorithm is able to perform this dimensionality reduction much better than the kernel PCA.
Okay, now we're going to the simulation of isomap. From the first, we import the isomap with scikit-learn package, and then we set the parameter with n component is 2. That means we reduce the data into 2 dimensions and enable 10. And then after that, we reduce the data, and then we try to plot the data in 2 dimensions, and we got this result. So from the result, we can see that isomap is able to reduce high dimensional nonlinear data clearly. Next, so what is the advantage of manifold learning? Okay, first, we may do it to save space by reducing the number of dimensions. 2, obtain savings and the 100 with almost no loss of information. And the last is to understand the data better. And then what is the disadvantage of manifold learning? Okay, first one, the computational is cost. And the second one is mostly nonlinear supervised manifold learning methods compute the manifold embeddings only at the first available training points, whereas the generalization to new points is known as the out-of-sample extension problem. And it might be difficult to achieve high performance in manifold learning for complicated tasks such as in computer vision. And the last is calculating the graph population and performing an agent composition in a quick and inaccurate manner will cause distortion in the global structure. And for the conclusion, other methods of dimensionality reduction fail to be successful on nonlinear space, like PCA. So manifold learning can be an option to reduce nonlinear dimensions. T-isn't and isomap as two of several learning manifolds that are widely used can help us understand the data better. Even so, manifold learning also has drawbacks that can be taken into consideration. So I think that's all from us. I hope this explanation has given us new insight to reduce nonlinear high dimensionality. And thank you guys.